Thank you for coming back. In this talk, I will discuss research from my lab, where we focus on how we can use DNA structure to pattern other materials. So this will be a little bit research focused. I'll try to explain the chemistry aspect of things. If you have any questions, do feel free to interrupt me. Again, I want to thank the people who. Okay. All right. We need to share the slides. Okay. Sorry about that. I want to thank the people who did the actual work. A lot of the research was pioneered by a postdoc of mine many years ago, Sumaid Surveyed. He joined my group 2010 and spent about 3 years in my group, developed many of the foundational work that triggered a lot of the later development. Two current graduate students also working on this project, Shubhanka Kundu and also Anamita Kumari. They are here and here. Shubhanka also recorded the video that I'll be sharing with you later in the afternoon, showing the experimental procedure used in our lab to fabricate these DNA structures and their characterization using atomic force microscopy. Okay, so in the morning, earlier talk, I already talked about the power of DNA nanotechnology, and in particular, I want to highlight the high resolution that can be afforded by those DNA nanostructures. We already can use those DNA nanostructures to create materials over multiple length scales from nanometer to almost micron. So I showed the Mona Lisa structure that is approaching micrometer by micrometer length scale. Within the DNA structure, if you think about the double helical structure that's 2 nanometer in size, if you make a turn, that's about 5 nanometer, and I consider that being the ultimate limit of resolution in terms of size. What I didn't emphasize in the earlier talk was the potential of low-cost fabrication, and this may sound counterintuitive because most people would think DNA is a expensive material. Now, I had the same kind of impression that DNA is expensive until I ran some calculations to find out how much does it cost to cover an area of 1 square meter with DNA. Now, the reason I say cover 1 meter area with DNA is in a lot of the experiments I'm going to talk about, we only require 1 monolayer amount of DNA. So only a monolayer amount of material is required, and that translates to very small quantity. So if you run the numbers, you'll find at the current rate cost of manufacturing, it costs about $1 to cover a square meter of area. So within the context of surface patterning, that cost is actually pretty low, and potentially can be even lower in the morning in the future. So the DNA template can potentially be a very low cost template even for large scale manufacturing. So that's something I want to emphasize. I already showed different ways of making the structure, so I'm going to skip those. A lot of the work, so here's the motivation. What kind of future big direction we're targeting? We're looking at two different kinds of future applications. One is in the area of nanoelectronics. And in this case, what we are concerned about is the patterning, doping, and the deposition of materials onto silicon and other semiconductor substrates. So here's a picture of Intel CPU. Now, if you look beneath those packaged structure, what you're gonna find is a lot of transistors, essentially, or MOSFET. Now, you're typically shown this kind of electrical engineering diagram, but on the chip, what you see are something like this. You have doped region of silicon, either p-doped or n-doped. You have gate electrodes, and you have gate dielectric, and you have interconnects. Okay. Now, this again is a cartoon. Now, if you look at the actual device, at the chip level, what you see is actually quite different. What you see are horizontal and vertical bar structure. Now, those bar structure actually makes it, those two pictures are equivalent. The bar structure defines the area of doping. It defines where the gate electrodes are, so on and so forth. So what it means is that if you can make a very simple geometric shape and a pattern on silicon wafer, and if you can make it over a large area, then you can make a lot of transistors. And from there, you can make memory device. From there, you can make logic device. But the first step of making that happen is you have to be able to etch silicon. You have to be able to deposit materials, usually conductor or insulator. And you have to be able to dope silicon. So those are the three fundamental steps of silicon-based nanofabrication. Now, why we're interested in using DNA to make transistors is simply because the current way of making transistor devices become more and more expensive. Now it takes about $5 billion to make a new fabrication facility. This is an earlier number quoted by Intel. The extreme UV stepper right now used in a lot of those fabrication cost over $100 million a piece. So this kind of investment would only make sense when you're making large-scale commercial fabrication. A CPU, a GPU, a large-scale memory, things like this. It becomes very expensive to invest and becomes expensive to make. There's another area of patterning we are interested in. That's what I call large-scale surface patterning, and those are completely different incentive. Instead of making smaller and smaller structure, and instead of making regular arrays of those structure, here we're interested in simply creating surface texture. We're not so much interested in making a regular array. As long as we have certain density, we'll be happy. Why this is interesting is because a lot of properties of materials are related to the surface texture. There are certain properties that have nothing to do with material itself. It only has something to do with how the materials are structured in three-dimensional space. Now, wetting is a prime example of this. If you have a porous structure, then when you have water droplet sitting on the surface, the water droplet actually got suspended by the air pockets embedded between the porous thin film. And when that happens, you will exhibit a superhydrophobic behavior, and that can be beneficial in a lot of applications. Imagine in the cold winter of Alaska, it probably is not going to apply to India. You don't have to worry about ice freezing on your and sticking to your car window. It can simply be brushed off very easily because they do not stick to the surface very well. Okay. There are recent example where people achieve superhydrophobic behavior using a superhydrophilic material. Okay, this is a silicon oxide material, but patterned into a very strange shape. This so-called double reentrance structure. It's like a mushroom. Okay, but it's made in such a way that the water droplet would have to go above to completely wet the surface. So this kind of surface makes the surface super hydrophobic, even though the underlying material is super hydrophilic. So again, this the transformation of surface property by using nanoscale texture. There are a lot of interest in so-called metamaterials. There you have metallic and or semiconducting materials shaped into very defined patterns, and those patterns can create interesting optical and magnetic properties, and in some cases can refract light and other magnetic wave in strange directions to the point that you can make certain objects invisible. So you could have cloaking effect by coating the surface with nanoscale and micron scale features. So in those applications, we are, as I said, we are more concerned about large-scale patterning instead of high resolution and high density and regular lattice structure. We simply want a lot of those shapes. We want them over a large area, whether they're in an array form or not a big deal. Okay, so this is the second part that our lab has been focusing on. So if I take a step back and think about the competition between various kinds of patterning techniques, there are more or less two different kinds of patterning. One is bottom up, another is top down. Right? By bottom up, you start with molecular material, and by encoding properties into their molecular structure, they can self-assemble into all kinds of interesting shapes. And in this area, the block copolymer phase separation is probably the most well developed, where you can design the block copolymer structure, sequence, molecular weight, so on and so forth, and they can automatically phase separate into different geometries and compositions. And there are also directed assembly approach developed to, for example, make the polymer phase separation domain into making 90-degree turns. Things like this has been done. Or to incorporate different periodicity into the block copolymer separation. And those are all very powerful techniques. Now, what the nanostructure brings, if you look at this diverse shape of patterning templates, it's kind of a combination, offers you a combination of bottom up and top down. With photolithography, you can make any arbitrary shape. With bottom up assembly, you can make regular geometric shape, but not really arbitrary shape. I can't imagine a way to design a block copolymer such that it phase separate into my initial. It's just impossible. But with DNA structure, it's pretty easy to do. If you can make a smiley face, you can probably make anything you want. Right? So with this in mind, we are broadly looking at applying DNA structure as a template for various applications, and I'm going to first focus on nanoelectronics related application, then I'm going to talk about large scale patterning. All right, so the story started about 15 years ago when I started my job at University of Pittsburgh, and I was interested in developing etching process that can be catalyzed by DNA. Okay. And why we're interested in this? Because etching is a fundamental process in nanoelectronics industry. You want to pattern silicon wafer, almost always involve some kind of etching. So we got interested in identifying ways to etch silicon oxide, but we want to do it in the presence of DNA such that we can transcribe the shape of DNA nanostructure into the silicon oxide layer. Okay. And this work was done led by my postdoc, Sumay Surveyed, and I didn't expect it to be working, but turned out to be working beautifully. So what I show here are atomic force microscope images of a DNA triangle that you're probably already familiar with. And those DNA triangles are deposited onto a silicon wafer with a thermal oxide layer. Okay. And the oxide layer is about 300 nanometers. What we did then is we flow hydrofluoric acid vapor over this DNA deposited wafer surface. And what we find was that there are two different outcomes depending on the reaction condition. In one condition, we can create, after the etching process, we can create nanoscale trenches on the surface. And the trenches, the shape of the trenches duplicates the shape of the DNA nanostructure template exactly. And in another case, we find we can create nanoscale ridges on the surface. So a totally different outcome. One is additional etching, another is less etching in the area covered by the DNA nanostructure. So naturally, we were interested in understanding what is happening. And if you think about this, here, the presence of DNA somehow changes the reaction rate on a very local basis. And you have to think about the geometry here. Here, each DNA nanostructure, the edge length is about 100 nanometer. And the width of this one edge, this triangle, the width of the triangle edge is about 25 nanometers. So this is a very high quality pattern transfer from molecular scale template to the silicon oxide layer. So what is happening? What is happening is a process catalyzed by water. So the etching of silicon oxide by HF is a well-known process and is known to be catalyzed by water. So this reaction will produce silicon fluoride, which is a gas, and water. So this is a classical autocatalytic process, meaning that the reaction would be catalyzed by its own reaction product. So a faster reaction would produce more water, and more water would make the reaction go even faster. So what this means is the reaction rate would correlate with the amount of water on the surface. Now we're doing everything in gas phase. We have silicon wafer with DNA on it, and we are flowing HF vapor, and we control the amount of water vapor in the gas phase. So there will be an equilibrium between water vapor and water absorbed on the silicon oxide surface. The presence of DNA would change the amount of water vapor absorbed on the surface because DNA can enhance water absorption under certain conditions and prohibit water absorption in other conditions. But also what's interesting here is because of autocatalytic nature, even tiny differences in the water concentration on the surface can be amplified by the reaction itself. So with that, essentially what we did here is we can use DNA as a catalyst to enhance oxide etching, but in an indirect way, because the role of the DNA would be a sponge. It absorbs water from the gas phase, and that presence of water would enhance the etching reaction locally. And in each of those trenches, there is a DNA structure sunken into it. Now, if we change the relative humidity to a different regime, if we run the reaction at a higher temperature, it turns out the DNA is not very effective holding the last bit of water. In that case, there's a competing process where DNA becomes a diffusion barrier, and that makes the overall reaction rate lower. So we can switch between these two by simply changing the reaction temperature, which changes the relative humidity of the environment. So with this idea being figured out, we look at a range of questions, and in particular, what is the ultimate resolution we can get? And the DNA structure turns out to be particular convenient for us to answer that question because the structure we use actually has a single-stranded tail of DNA. This is about, I think, 70 to 100 bases long. It just hangs there, and there's no double-strand structure. That's by design. And what we find is in at least some of the etched structures, we find this small tail in the transferred pattern, and that indicating that even a single-stranded DNA is capable of delivering this catalytic effect to the substrate, and you can essentially carve the shape of a single-strand DNA into a silicon oxide substrate. We are able to get around 10 nanometer, 15 nanometer lateral resolution, and we can make pretty deep trenches up to 11, and later we can push this to even 20 to 30 nanometers deep. And the etching selectivity is at least 3 to 1, so the presence of DNA would enhance the etching rate by a factor of 3. More recently, we started to think about ways to incorporate or modulate the etching rate. And the thought process here is that because everything is controlled by water, so what can you do to change the amount of water on the surface? With a background of DNA plate, you can add additional material, a protein in particular, because a lot of protein, their external surfaces are hydrophilic. So we are able to show that by modifying DNA structure with streptavidin, this is just a convenient protein for us to use, we can make the etching a little bit faster in the area being modified with streptavidin. And by doing this, we can create a pseudo 3D fabrication instead of just doing a 2D fabrication. And to characterize this, we end up have to use a polymer replication process because the trenches are actually too deep for the FM tip to probe the bottom. Some of the images I show are actually the replicated polymer substrate. And this shows you the general picture here, and I want to highlight this one. This is the triangle-shaped DNA structure, but with one side of it modified with proteins. And you see on this one, this is the contrast enhanced. You see one edge is more blackish in a red background. Without contrast enhancement, you don't really see it in the regular color scale here. But once you change to a different color scale, you find a lot of them are one side modified. And in the histogram, you see one edge is higher than the other two. So with this modified DNA structure, we are able to conduct the etching, and this is the polymer replica. Again, here you see one of the edge, this one being higher than the other two. And if you look at the histogram, in this case, we're etching as deep as 25 to 30 nanometers. With the modified structure, we see about 10 nanometer enhancement of etching depth. So on the edge that has not been modified is about 25 nanometer. After modification, it's about 35. This one shows a high resolution image on the polymer replication. And again, a deeper trench becomes a higher ridge because it's inversed. Here you see one side is higher than the other two. All right, so another process we've been interested in is to think about how to make a conductive nanostructure. You'll recall the overall scheme we have to accomplish. One is etching. Another is some kind of deposition, and the deposition oftentimes involve conductive substrate because you have to create conductive wires to wire up different nanoscale electronics. So at one point we got interested in figure out whether we can convert DNA structure into a conductive carbon material. And this may or may not ultimately solve the need for nanofabrication of electronic devices, but I thought it's a interesting example of how an organic nanostructure can be used as a precursor to make inorganic materials. So what we demonstrate here is that DNA nanostructure being organic, you can view them as feedstock. And if you coat the surface with a thin layer of oxide by atomic layer deposition, we can trap the organic material in the matrix. And once we do that, we can heat everything to high temperature and carbonize all the organic material. And that turns the DNA into carbon material. And those carbon materials are conductive, as we shown by conductive atomic force microscopy. So this shows the DNA nanowire template we used, and then we coat the nanowire with atomic layer deposition. Now the coating is pretty thin, so everything is conformally coated. So if you look at the atomic force microscopy image, you don't really see anything different. You still see the same kind of nanoscale feature of DNA nanowire. What you do not know is there's a 20 nanometer thickness of coating on it. We're able to show that after annealing, if you look at these two images, these two are taken at the same time. This white square, okay. After the annealing, we took the AFM image at exactly the same location. And you find the patterns are still the same. So the annealing, the high temperature annealing doesn't damage anything. And we also removed the silicon aluminum oxide coating to expose the underlying carbon nanomaterial. Again, the two images are taken at exactly the same location. And I want to mention this is very, very difficult to do. It took my students quite an effort to relocate exactly the same location on this. If you think about the silicon wafer we use, is several centimeters in size, and somehow you have to find the same area within a micrometer, 100 nanometer precision. Okay. But the message you can see here is that those two patterns are exactly the same. Okay. So whatever was DNA is now being converted to amorphous carbon material, and we did conductive FM and showing that those materials are conductive. And more recently, we started to think about the doping, because doping is a fundamentally important role and component in semiconductor fabrication. And we're thinking how we can dope silicon using DNA and how we can change the doping concentration by manipulating the molecular chemistry of DNA. So related to this, many years ago, we studied how the DNA nanostructure would decompose under very harsh conditions. And there we find a very unexpected conclusion that once you deposit DNA nanostructure onto silicon, there are actually the shape of that is actually very robust. So as an example, here we have those triangles on silicon wafer, and we subject to UV ozone oxidation. This is a very harsh oxidation condition that pretty much guarantees removal of all organic materials. And that's our expectation as well. However, if you look at the AFM image after 20 minutes of exposure to UV ozone, you find the surface is still full of those triangle features. Okay. Now, we know that the 20 minutes exposure actually got rid of all the organics. And the triangle shape, if you look at the cross-section, actually has a much reduced height. So we are actually indeed removing the organics. What is left is the inorganic material. And what is amazing is that those inorganic residue maintained the overall shape of the DNA structure. This is, in retrospect, is not very unexpected because on a solid surface, the diffusion is going to be very slow if there's no water or liquid to facilitate the diffusion. So the phosphate residue, because the DNA has phosphate backbone, and that phosphate backbone is not going to vaporize in a typical oxidation condition. So the phosphate would stay behind in the form of phosphate, metal phosphate, and that phosphate would stay behind and in the same shape of the DNA nanostructure. So with this in mind, we start to think about ways we can leverage the phosphate residue for doping. And the reason being, phosphorus is one of the most common dopant used by silicon industry. So phosphorus has 5 valency electrons, silicon has 4. So you can dope phosphorus into silicon, that will make it into N-type doping. Okay. So that's what we did here. We deposit DNA structure onto silicon. Now this time there's no oxide layer. We get rid of the DNA, organic portion of DNA, and we were left with residues. We coat it with a layer of silicon oxide, and the intention here is to limit the lateral diffusion of the phosphates. And then we heat it to high temperature using a process called rapid thermal annealing, RTA. And what happens in this here in the RTA is under intense temperature, about 1,000 degrees Celsius, there will be a solid state reaction between phosphate and silicon, and that reaction will produce phosphorus atom, which then diffuse into silicon to dope the silicon wafer. What's unique in this process is that the doping would only happen where there's a DNA nanostructure coverage. It will not happen when there's no DNA. The doping density is also a function of the amount of DNA base pair, because one base pair translates to 2 phosphates. So if you have a single layer DNA nanostructure, it will give you lower doping density compared to the case where you have double layer or tri-layer DNA nanostructure. So this gives us a way to modulate the doping density in one batch of doping process. Okay. Now in the traditional nanofabrication process, each doping step will only give you 1 doping concentration. Okay. We also tried an alternative method where we use sulfosym monolayer to inverse the polarity of the dopant. So with DNA, you can do N-doping because there's phosphorus, but that's the only dopant you have in DNA. To achieve P-dopant, usually you would need something like boron. Okay? But there's no boron in DNA material. So what do? Instead of doing it directly, we deposit DNA onto silicon wafer. We grow a sulfosym monolayer. Now in this case, the DNA would block sulfosym monolayer happening everywhere. And we get rid of the DNA and then refill the gap using a boron-containing sulfosym monolayer precursor. So now we can create a patterned sulfosym monolayer where there's a boron-containing molecule at where the DNA nanostructure is being deposited. And we can do the same rapid thermal annealing, and by doing that, we can create a doped area where the doping is boron in nature instead of phosphorus. Okay, so with that in mind, I want to show you some actual data. So here we used a wire-shaped DNA nanostructure. It's easier for us to demonstrate the case. So this is this is after the DNA nanowires are deposited on the surface, and then we expose it to UV ozone, and what you see is the height of the structure become much less, and that's because you're oxidizing the organic portion of the DNA. Now, after the doping, what we find are 2 changes in the AFM. When we look at the topography, we start to see a lot of trenches on the surface. And if you recall the message here, there's some kind of solid state reaction that etches silicon. Now, if we look at the surface potential using Kelvin probe microscopy technique, we find there's also contrast in the surface potential. And this is one of probably the strongest evidence indicating that the silicon is being doped. So the contrast here is not due to topography, but rather a change of surface potential, which is a function of dopant type and dopant concentration. Okay. So with the the doping process figured out, we collaborated with a research group in electrical engineering, and we evaluated the doping process in the context of fabricating nanoelectronic devices. And here we made some very simple devices, a PN junction, we have a diode, and what we did is we simply deposit one contact on top, and we use the silicon the silicon as the back contact. And in this case, we start with p-doped silicon, and then we dope with excess amount of phosphorus. So this is an inversion of the doping profile, and that created the p-n junction in this vertical direction. And we can make diode structure, and by measuring the IV curve, we find this fits our typical idea of p-n junction. The conduction is one direction, but not in the other direction. A control device showed no particular non-doped device showed no leakage current based on our fabrication technique. Okay. We also fabricated more complicated structure, three-terminal field effect transistor device. Here we start with a DNA nanowire, and we dope an intrinsic silicon wafer. So in this case, there's no doping to begin with. Again, we dope it with N-type dopant phosphorus. And we use conventional lithography technique to define a field effect device in the middle. And this is the actual device with wire bonding. And if we measure the conductance of this channel, we find the conductance goes up significantly. That's the red. Up to remind people that this is voltage as a function of current. It's the other way around. So a flat line indicates high conductance. Okay. And a sloped line indicates low conductance because this is the voltage drop after applying this amount of current. So it's the opposite of RV curve. This is a VI curve. Okay. But this shows that after doping, the electrical conductance got greatly enhanced, something you would expect. We also conducted gating measurements. So this is a transfer curve where we look at source drain current as a function of gate voltage. And what you see here is the modulation of source drain current as a function of gate voltage. And that, again, is what you expect for a functioning transistor device. Now, if you look at the data, you'll realize that we're actually cheating quite a lot. The bottom is not zero. We're not turning off the transistor. Okay. We're actually, if you look at the actual modulation, it's actually pretty small. It's from 1.8 to 1.9. We're looking at 5% modulation, which is not a great device. And we're not claiming it's a great device. What is exciting in this device is that we show using DNA, you can dope a silicon wafer with nanoscale confinement based on the shape of the DNA structure. And from there, you can actually make, not meaningful, but you can make proof of demonstration device. And certainly, if you look at this one, this is a much better device characteristic curve based on typical expectations from electrical engineers. So there's still a long way to go. Now we have ways to do etching, we have ways to do doping, and the rest of the question is how can you make instead of one. So here, all this wire bonding is for one device. This is fine for a research purpose because we want to figure out whether we can make one device, and the answer is yes, we can make one. Now the next step is, can you make 10,000? And that's something we want to accomplish in the near future. And if we can make 10,000, that means we can probably make a logic unit of a computational unit. So the smallest CPU, the 4-bit CPU, would require about 4,000 transistors. Now, if you think about the Mona Lisa figure, that's about 800 by 800 nanometers in size. Now, if you also think about what is the smallest feature you can create within that big chunk of space, I would say about 10 nanometer by 10 nanometer easily. Right? So if you do the math, you'll see that within that Mona Lisa, figure, if we change the pattern instead of making Mona Lisa, what if we change Mona Lisa into a mask of a 4-bit CPU? How many transistors we can make? We can potentially make 80 by 80 devices, and that's 6,000 devices using one mask of DNA template. If we can do that, I think that will transform the way people think about nanofabrication, especially nanofabrication using bottom-up approach. All right, so with the rest of time, I want to discuss a totally different direction of nanofabrication. And this would be a case for large-scale application. And I would call them probably cheap application. Here we are way more interested in cost, how we can reduce cost, how can we make it really cheap so that people will actually use them. The story started with the same kind of DNA template oxide etching that I showed you before. Except the interest here is not making a highly precision shape, but rather all we want is to create nanoscale roughness. And to some extent, we also care about exactly what kind of nanoscale roughness needs to be created. But at higher approximation, as long as we can create nanoscale roughness and we can create the dimension of those roughness, we'll be happy. And with DNA template, we can certainly do that. So here I show different silicon wafers, not subject to any HF etching and subject to HF etching, but without applying any DNA templates, and also subject to HF etching using different surface coverage of DNA templates. What you see here are certainly different degree of surface nanoscale roughness. What we find is that a rough surface at the nanoscale produce less adhesion of bacteria. This is, again, nothing new. People know this already. And the data is shown here. And what you see here are the silicon wafers, those 4 different samples. We incubate them with different kinds of bacteria suspension. After a couple of hours or after a couple of days, depending on the experiment, we take it out. And we basically look at how many bacteria are being absorbed onto the surface. And if you look at the data, so those are all stained. So each dot is a bacteria, essentially. And in some cases, they aggregate. In other cases, they don't. Okay. And there are 2 different channels. One bacteria. So if you stain everything with PI, this is one dye that only stains dead bacteria. And Cyto9 stains both live and dead bacteria. So what you see is the great reduction, you look at this too, the very significant reduction of bacterial adhesion to the surface. And that is entirely due to the nanoscale roughness, because bacteria has a dimension of a couple of micrometer. And when they come to the surface, they have to have effective interaction surface area for the bacteria to stick to the surface. And once you make the surface nanoscale rough, you reduce the effective contact area, and that translates to reduced bacterial adhesion. And this reduced bacterial adhesion can be beneficial in a lot of contexts, in particular medical device, implants, catheter, for example. You want to reduce bacterial adhesion on the surface so that infections and a lot of other undesirable medical complications can be reduced. This again is a long-term study showing that not only the initial bacterial adhesion can be reduced, but the biofilm growth, this would be the long-term outcome of bacterial adhesion, you grow bacterial colony on the surface, and we were able to show that a high density of the DNA nanostructure can produce the kind of nanoscale texture that reduce also the biofilm formation. Okay. So that is one direction in the context of biological material or medical device. Now we are looking to even cheaper ways to expand the fabrication into other materials. Silicon oxide is good for proof of demonstration, but you're probably never going to find a medical device made of silica. So what we're doing now is to reproduce everything we demonstrate here on a polymer substrate to show that polymer substrate can also be patterned by DNA nanostructure, and their nanoscale morphology also translates to anti-fouling behavior. Okay. We are also looking into ways of applying this surface texture trick into modulating optical properties of surfaces, and in particular reflection. This has a lot of relevance in everyday consumer electronics. If you pull out your phone, and a lot of times you'll see this glaring if you are viewing your phone or your TV under bright sunlight, and you're probably very annoyed by the strong reflection. And how can you reduce that reflection? One way to do that is to, again, create surface texture. So reflection happens when you have a sudden change of refractive index. However, if you create a gradual change of reflective index, then reflection will not happen. And that's the foundation of many anti-reflective materials. And here we show that we can use DNA structure. Those are, again, those triangle structures. We don't really care what kind of structure we use for those experiments. We only want to show a proof of demonstration. And it just happened that this triangle structure has been very convenient for us for a lot of applications. So we were able to show that we can, in addition to doing the etching, we can also do additive manufacturing, depositing all kinds of oxide material onto the DNA nanostructure. And from there, we can conduct conventional plasma-based etching, and that produce high aspect ratio structures. And you'll find a lot of those triangle, there are columns now. You're looking in the scanning electron microscope, looking down, and looking at the optical performance. The nanostructures that has been patterned by the DNA, the blue curve, shows much reduced reflectance by about 40 to 60%. Okay. And the control samples is at 100%. And if you just deposit DNA mask but not doing the etching, pretty much no change. Okay. All right, so I just mentioned that we're interested in pattern polymer, and with a DNA structure, we tried a different approach. Here we demonstrated that you can use DNA structure as a stamp, as a physical stamp, to imprint its shape by mechanical force, to imprint its shape onto polymer. So on the top, again, are those triangle structures that we used. And on the bottom are polymethyl methacrylate polymer surface. And those polymer surfaces show the negative imprint of the triangle. And those are done by spin coating the polymer onto the silicon wafer with triangle deposit on silicon wafer. We then peel it off, and somehow the shape of the DNA got transferred to the polymer side. And you'll find in many cases the quality of pattern transfer is very high. The DNA structure here are actually made of 3 edges, and there's a small gap between each of the edges, and you can see somehow, you can see that small gap being reflected on the inverse replica. So with that in mind, we started to think about more direct imprinting techniques. So one direction we're going right now is to study how DNA structures can be directly deposited onto polymer. And we have some initial success, but not quite a lot. DNA nanostructure is very hydrophilic, and most of the polymers are hydrophobic. So traditionally, people didn't think about those two are compatible. But our recent work, still unpublished, seems to suggest some kind of hydrophobic interaction and incorporating charge-charge interaction can stabilize the DNA structure even if you are working with a hydrophobic polymer substrate. So with this kind of process in place, we may be able to work with DNA structure templates on a wider range of polymer substrates and develop etching and deposition reactions directly on those polymer substrates. So with that in mind, I think I'll stop. To summarize, I hope I convince you that DNA templates can not only serve as a high precision fabrication process, but can also work very well in areas where low cost is also important. We have used DNA nanostructure in a variety of template substrates. We spend a lot of work on silicon oxide, but the more recent work suggests that even organic, hydrophobic organic templates, substrates are also compatible with DNA nanostructure. Again, there's a lot of counterintuitive results there. But hopefully you'll see DNA now as a more, it's more than a genetic material. We still use a lot of this genetic encoding technique to control the shape, to control the properties modifications, but you can also view it as a structural material. Especially in the nanoscale, it can be a particular interesting structural material to define the chemical reaction and to encode geometric information. So with that, I thank you again for being here, and I'd be happy to answer any questions.
To deposit nanoparticles on a silicon wafer, as Professor Hetao has explained that how we can use DNA as a platform. First of all, we can introduce nanoparticles on a DNA and then put that DNA on the surface of silicon wafer, and then we remove the DNA by either UV or ozone oxidation, so that only the nanoparticle would come on the surface of the silicon wafer. So it can be used as a platform. You may ask questions, anything related to the fabrication, how this can be done, what is the cost maybe, what is the cost of, Professor? How economical is it to use DNA as a...
Yeah, that's a very good question. So when I started my independent career, I thought, oh my God, this is going to bankrupt me in a couple of years. So we ordered a batch of, those triangle structure, those are made by the origami approach. We bought one batch of those 300 DNA strands from IDT. I don't know if they have a branch in India, but it's a popular vendor for custom-made DNA strands. So we spent about $3,000 on those 300 strands. We're still using them today, and that was ordered 15 years ago. So it's very economical. Yeah, we more than, actually, if you do the numbers, the scaffold strand is actually way more expensive. But because a lot of the work we do is about monolayer amount of material, and each experiment only consumes wafer chips, just a small wafer chip about 2 centimeter by 2 centimeter. The amount of material we consume is actually minimal.
Give her the mic. Give her the mic.
If we have more complex DNA based material, then how can sequence specific interaction can be optimized? If we have more complex DNA based material, then how can optimize sequence specific interaction?
So the question is, if we have more complex DNA material, how can we optimize sequence-specific
Interaction,
interactions?
yes, sir.
Okay. Thank you. So the sequence parameter space is always going to be limited by the available, I guess, well, the more DNA material you have in one structure, the more likely you're going to encounter certain sequences. For example, in the context of making the origami structure, you have 300 unique sequences, and that certainly would limit on what new sequence you can use because you want to avoid, duplicating the same sequence that is already there. That can be a problem, but usually, even for the typical origami structure, we're only talking about 300 unique strands. If you think about each strand is about 20 to 40 bases long, the parameter space is actually huge. We're talking about 2 to the 20 or 2 to the 30. So in that case, it's still not limited by the parameter space. It's not a real problem yet. Um, of course, if you are going to create a larger structure, it will become a problem. A benefit of the structure is a lot of the sequences are being protected, so to speak, because they're a double helical structure. And if there's no niche, then strand displacement in a lot of cases are pretty slow. So even if you have conflicting strand sequence, sometimes it may or may not really impact your work.
So, what are the challenges in scaling this technique?
Can you repeat?
So, what are the challenges in scaling this technique?
The scaling. So there are a number of, areas. One is the DNA material itself. So there needs to be a large production of DNA nanostructure available so that people can actually use them. There are a couple of companies already selling different kind of DNA nanostructure. Now, if the application is 2D related, then I think in most cases the cost is not a real big issue. However, DNA is still expensive if you are calculating things on a mass basis, by a per gram basis, DNA is still quite expensive. And that is in the context of our, machine-based DNA synthesis. There are ways to go around it. For example, you can do fermentation. You can use biotechnology to produce libraries of DNA strands, and from there you can, make DNA structure. That has been done. So you can grow bacteria essentially, and the bacteria will spit out DNA structure. So there are ways to mass produce those structure, but I have not seen a killer application yet. Um, those are all new technology, a lot of exciting things that can be done. But is there a commercial product that has to use DNA structure? I see a lot of justification in the lab, in fundamental research. It can provide a lot of benefit. But in the industrial setting, I have yet to see a strong justification. So we still are looking for a good application that justify the use of DNA nanostructure. what kind of so. So the question is potential application of DNA nanotechnology in packaging application. Do you mind elaborate what kind of packaging you're looking or what kind of potential use of DNA nanostructure in that context? See. Right. So antibacterial packaging. So in that context, I think again, my view might be biased. I see some role of creating surface nanoscale texture to make the material intrinsically bactericidal. So for example, if you create a surface where there are a lot of sharp needle-like structure, can you make the surface, in that case, killing bacteria on contact, because there'll be surface tension force that can apply to bacteria so that the needle-like structure could puncture a bacteria on contact. Now, that kind of concept has been demonstrated in some surfaces, like silicon in particular. Now, can you apply that to another material that people use in packaging? Probably and maybe, but I do not know exactly how that can be done. Um, if if you are thinking more along the line of chemical-based antibacterial, then antibacterial surface, then I don't see a strong justification of DNA nanotechnology there. Conventional organic chemistry, surface coupling, things like this might be more useful or straightforward.
One more question.
So, what are the applications of DNA origami?
Uh,
Applications of DNA origami.
you are asking the application of DNA origami.
Yes, sir.
Okay, I I think I elaborated a little bit more on this side in the previous talk, but briefly, I would say the uniqueness of this class of material is the ability to define its shape and define material composition and the position. So whenever you have an application that requires a precision placement of molecules or materials, DNA structure become relevant. So in that context, any lithography, any patterning would make sense. Any energy transfer related application or cascade enzyme catalysis would become relevant. Um, what else? Sensing, and especially in the context biological system, because sometimes you want the precision placement of different receptors or the same receptor but in a particular array form. And sometimes this kind of arrangement can trigger biological reaction and produce downstream cascade biological signaling. So those are the broad range of applications I think would justify a strong justification of DNA nanotechnology involvement.
Sir, what are the limitations of DNA-based nanoelectronics?
So the question is about application of DNA-based.
No, sir, limitations. Limitations of DNA-based.
Limitations. Okay. So limitations of DNA-based nanoelectronics. I would assume you're asking for DNA-based fabrication of nanoelectronics. That's a very good question. So I didn't get a chance to talk about the downside, but if you, well, I think I mentioned some of it, but if you look at the example I showed here, we're talking about one device. Right? Now, if you look at the motivation slide I showed, this CPU has probably a billion of devices, probably even more. Okay. Now, and in this case, the devices are in array form, so you have an array of transistors, especially when you have a memory, you have an array of capacitor, you have an array of 2-terminal, 3-terminal devices, and you have to do this over 1 billion times, and every time it just works. Okay. Otherwise, it's a disaster. Now, semiconductor industry is able to do this after 56, 70 years of refinement, and the DNA technology is not there. So the first order challenge I see it is a large area fabrication of device array. How can you make an array of device, and even before that, how can you deposit DNA structure template into a regular array with minimal defect? There's no good answer and no good solution to that. Some people already work on this and they have very creative solutions, but from an engineering perspective, the solution is not there. Okay. In addition to that, a lot of those devices, they require multi-step fabrication. With the DNA template, we're not there yet. We're able to do one-step fabrication, and the DNA nano templates are gone. Now, if we're going to do another step of fabrication, we have to make sure those two steps are aligned. That, again, is a big challenge. How can you deposit DNA structure to the same location so that you can do, for example, one step of etching, another step of doping, and then third step of deposition, and somehow everything just aligns with nanometer precision? Again, there's no good solution. So there's a lot of challenges, and maybe that might be a shortcoming and issues that I didn't get a chance to elaborate.
Sir, how significant is the type of DNA and the source from which it is obtained?
Can you repeat?
How significant is the type of DNA and the source from which it is obtained?
You are asking the type of DNA
and the source from which it is obtained.
So all the approaches that people use here, in this case the bacteriophage DNA is the long strand, so that's biological in nature, and all the short strands, they are synthetic, made by automated DNA synthesizer. Okay. Now you can certainly, DNA is DNA. That doesn't matter which source it's coming from, it's still the same. So as long as the sequence is the same, doesn't matter how you make them. And there are ways to make all the components from bacteria fermentation process by regular standard chemical biology approaches. That's not a problem. The future and sorry, the last part I didn't catch. You're asking the future and direction of DNA nanotechnology. That's a very big question. Here's my very limited perspective. I see two strong justifications. One is very fundamental research where cost is not an issue. In that case, you can justify using very expensive templates to create the kind of distance information you need to advance basic science understanding. Okay. That can involve, cascade catalysis using enzyme and other things. That can include precision distance-based measurement of energy transfer, so that you can obtain very useful fundamental understanding of your material system. Drug delivery can have some future, I think, but it needs to be the imaging and drug delivery. The biggest hurdle I see is the stability and biocompatibility. But with that in mind, DNA structure can be converted into many other things. So you could just be using DNA structure as the first step and then produce some other carriers that better suits your need. Other than that, I see the high resolution patterning may have niche applications because this can be a way to, if you combine top down and bottom up, this can be a way to pattern high resolution features at much lower cost. And certainly my own hope is that the low cost application can materialize in the future. We've been pushing really hard in those directions, but because I'm working on that, maybe my view on that is also biased.
Anyone else? Want to ask question? Anyone else?
So my question is, in fabrication, what kind of interaction exists between inorganic phosphates of the DNA and the silicon dioxide? So,
oh, very good question. So the question is, what is the nature of the interaction between the phosphate and the silicon oxide substrate? So there are a range of the different contexts. So first of all, when the DNA structures are deposited from solution to the surface, there is ionic interaction between the phosphate and the silicon oxide surface mediated by magnesium. So phosphate is negatively charged, but silicon oxide solenoid surface, when it ionizes, it will produce silicon oxygen minus. So the surface of silicon oxide is also negatively charged. But somehow these two negative charged species do come together. And the reason being, when you do the deposition, there's a high concentration of magnesium 2+ ion in the solution. So the magnesium 2+ serve as an ion bridge. So silicon, oxygen, magnesium, and then phosphate on DNA. Okay. So that interaction turns out to be important in controlling the degree of surface coverage. And I think it also helps to maintain this morphological stability of DNA structure. Now, after the deposition, once everything's dried, then there's no mobility per se. And if you remove all the organics, I would assume that it's just inorganic small clusters of magnesium phosphate, deposited on silicon oxide. Thank you.
For a very insightful lecture. Please give a huge round of applause for Professor Hitao.
We're down here in the morning. Okay.
We will start your tutorial after that.
Yes.
And have some rest.
Yeah. So I'll.
If you want, you can remove the
So
cover.
yeah. So I'll have. I need to copy everything. I have a very large video. I have to copy to the computer.
Okay.
So I have a 15 minutes video,
And then
and I have a couple of slides explaining what students are doing.
you can do so.
Yeah.
During the lunch hours. Today, because I have another presentation.
Okay.
I'll give that presentation.
Okay.
Me and Dr. Asfar.
Okay.
And during the lunchtime, we'll transfer all the stuff.
Yeah. Okay. Do you want to